Okay. So, uh, for the online participants, am I audible? Am I audible?
Yes, yes, you are audible.
Yes. Right. So we were looking at complementation of ABW. The idea was that like if you have an ABW, then you can uh, look at it as an ACW, Kobushi automaton, by dualizing the uh, acceptance condition as well as by dualizing the transition functions. And then we saw that like you can translate the ACW to an ABW. It's actually a weak alternating automaton, right? And when you are going from ABW to ACW, then the complementation of the language that happens. And here it's just a translation from ACW to the weak alternating automaton. So what was the okay? And when we did that, this translation, there was a quadratic blow up here in this part, right? And what was the definition of a weak alternating automaton? So we saw that the set of states, so that was partitioned, right? Partitioned, and how it was partitioned, like so each part was either an accepting set or it was a rejecting set. And then there was also a partial order on the state space, in the sense that transitions lead you from one state to either a state uh, at the same level or to a lower one, right? Uh, right. And we also saw that like every infinite path, it gets trapped within some keyword, right? And so you can actually look at the weak automaton as either a Bushi or a Kobushi automaton. So often we don't say whether it's a Bushi or a Kobushi, we just say it's a weak automaton, right? Right. So if you have a WA with acceptance alpha, you can also look at this as a Kobushi acceptance Q minus alpha, where I'm saying that this is like a Bushi acceptance alpha, same as Kobushi acceptance Q minus alpha. Okay. So we saw this translation where you have the quadratic blow up. So it's similar to that, the construction of the I mean, when I say similar, it like borrows several ideas that we saw previously, which is about complementation of non-deterministic Bushy word automaton. Okay, good. So let's now look at some of the things about alternate alternating Bushy word automaton. So it's kind of um, we will see that these are exponentially more succinct. Like we already saw some example, right? If you recall, what was that example? There were these three contiguous i's, right? Where I belongs to that alphabet. So the alphabet is like sigma n 1 to n, and then you say that the language should have all those words where for each I you have like three contiguous i's, right? And then we did not formally prove, but then we say that like if you have to consider an NBW, non-deterministic Buki word automaton, then you might need to remember all the subsets which you have already seen so far, which possibly will give you an exponential shell blowout. Okay. Uh, Sometimes it may also be the case that though ABW are that way, they are succinct. They are more succinct, right? In the sense that this language you can express with a much smaller alternating Buki word automaton. Whereas the NBW is going to take like more number of states, maybe exponentially more states, right? And sometimes when you need to reason about ABW, they may also be, on the other hand, slightly more difficult in the sense, suppose if I tell you, like, how do you check the non-emptiness for ABW, right? How would you do that? For NBW, it's quite clear. I mean, we did that. Like, so you have, for example, there is an initial state. So there should be like, there may be several initial states, but from some initial state, you should have a path to an accept to a good state. And then from that good state, there should be a loop, right? And the actual, the labeling on the transition, so that is the letters, it does not really matter for the for the NBW. Now, can you really do such a thing? I mean, such a simple algorithm if you need to check whether a given ABW is non-empty or not, right? How would you do that? So suppose if you say that, well, I mean, if you have a path to such good state, and if there is a loop, and you say that if that is the case, then it is non-empty and vice versa. So is that statement going to be true? What do you think? For ABW, can you do a similar such argument?
We finally want to reach some true value in ABW.
True value.
Right? Like,
no, in ABW
or
also we have the
can
alpha
set
splits, right? We also have the alpha splits. So either, yeah, either you want to reach some true, or you want to see those alpha states infinitely often. So the way we looked at the NBW non-emptiness, does the same thing, does it work?
I guess if the transition has a false, or the formula is false, then it might not
And such a
work.
transition would of course not exist. I mean, you can sort of think that there doesn't exist a transition with a that corresponds to a false formula. Okay, so you can say that
Because there is no negation.
such
Okay.
formulas do not exist, right?
Yes.
So even if you have that, can you really say that the non-emptiness will work in the same way?
I don't think so.
You don't think so? Why?
Because now, like earlier, we had like a path, but now we are having like trees. Now we have to keep track of many trees. So I don't think that's gonna.
but we always
So a tree is a run. A tree is a run. As long as you have a single run which is accepting, it's fine.
But then in that tree, we want to keep seeing whether alpha states are visited infinitely often.
we finally need to look at this.
Some.
So but a tree might have a for all node, and for that
Correct.
we need to check both
All the things. I don't.
All the things. And what is tricky there? So what is the sort of the non-trivial part there? Like you have to look at all the successors.
Yeah.
And the thing is that all the successors, so what is important here is that, like suppose you have a delta of q comma a is q1 and q2, let's say, right? So suppose if you have something like the following, that delta of q comma a is q1 and q2, right? So what does it mean? It means that from q on a you go to q1, and on the same A, you also go to Q2, right? Now, if it happens that just by the mere fact that if it happens that you are able to see some alpha which is visited infinitely often, right? And it's also important to ensure that uh, when you are when you have another particular let's say successor that you are visiting, right? You cannot get rid of the label here, in the sense that both the successors. So when you have to accept, if a word is accepted, that word has the same label for all the corresponding to all the successors. Okay. So even if it is the case that you go here and then suppose there are some alphas you are actually seeing infinitely often, and maybe there are some alphas which you are seeing here infinitely often, but maybe this transition was not on A but was on a B or something, but then this is not sufficient. So just by the fact that you can reach some alpha and then you can see that alpha infinitely often, like there's a loop on that alpha, is not sufficient, right? So it can give a one-sided error. When I say one-sided error, what does it mean? It means that like the fact that if there is no path, then of course you know that the language is empty. If there is no path to a good state and if you don't find a loop on one of the alphas, then you know, of course, that the language is empty, right? But on the other hand, just the mere existence of a path to a good state and having a loop doesn't imply that the language is non-empty. Okay, so the non-emptiness checking directly is not that sort of trivial on the ABW. So what one can do is like to translate this into an NBW, and then you check the non-emptiness of NBW. Okay. So when I say that you need to translate it into an NBW, then you have to make sure that well, that I mean there indeed such a translation exists, right? On the face of it, it seems like syntactically the ABW is more powerful because it allows you to have some, more richer kind of structure, right? The ABW, it allows you to have these different kinds of, I mean, the transition is more, function is kind of richer, right? And, but what we are going to see now is that indeed you can like remove the alternation. So you can, there exists such a translation which removes the alternation, and you can translate, given an ABW, you can translate it to an NBW. Okay, so given an A, you can get an A prime. Okay, which is an NBW, right? So what is the idea? So the idea of this NBW is that it's going to guess a run of the ABW. Like, I mean, that's kind of the common thing, right? Like whenever there's a non-deterministic bookie automata or non-deterministic automaton, it's going to guess a run. Okay, and so the ABW can have multiple runs, right? Each run is a tree here, and this is going to guess one such run. So what should be the intuition here now when you say that the NBW is going to guess a run? What is the intuition that you would have? Like in a tree, you would have several states, right, at the same level. And in the case of NBW, what would you like to store ideally?
Like sets of states.
Sets of states, right? I mean, which is also what you would do when you are translating from a non-deterministic, say, NFA to DFA. It's kind of a subset construction. But there is something more to that. You also have to ensure that, in some sense, that there is a notion of an acceptance, which is different from automata over finite words. Like you would like to visit these good states infinitely often, right? So how do you, okay, so how do you think you'd like to, so your idea is, the intuition is correct, like, so at every level you'd like to see in the run what are all the states that you are visiting, and you'd like to keep track of all these states at every level, but then you would also like to see that uh, that across all the runs, all these runs are visiting the good states infinitely often, right? So yeah. So yeah, I mean, I think I can, if I give you a bit of a hint, you should be able to sort of this construction is not too difficult. By the way, this construction is called Miyano-Hayashi construction. Miyano-Hayashi. I don't exactly recall the year. Should be around sometimes we also call it a breakpoint construction. breakpoint construction. I think around 87 or so, but yeah, right. Okay. So it guesses, so the A prime guesses a run of A, right? A run of A here is actually, you remember that it's a tree, right? And so it keeps track of uh, all the states visited at a particular level, right? At each level it, or yeah, at each level it does so. And and also we need to make sure that all paths in the run tree of A, they visit, all paths visit the good states alpha infinitely often. Good states alpha infinitely often. Right? So this is what we would like to have. Okay. So in particular, A prime keeps track of states which owe a visit to alpha, right? So essentially what I'm saying that you have the run, so there are several paths, and then I would like to say that you would like to keep track of those paths which are yet to visit the alpha, right? And once it has visited the alpha, you sort of kind of reset. When you know that all the paths have visited the alpha, you kind of reset, and then again you keep maintaining that which of them are yet to visit the alpha. So you will keep track of the ones which have not visited the alpha yet, right? So the state space is going to be of the, like as you said. So it's a subset of the states that you have. So it's like 2 raised to q, and I'm also going to have another 2 raised to q. So this part will keep track of this thing, the set of states which owe a visit to alpha, in the sense the ones which have not visited the alpha yet. And once they have visited the alpha yet, then you say that you can remove those states which have visited the alpha states, right? And so if you see that the runs are going like this, and at some point of time, if you say that if so it can happen, right? Like so you have the path, right? It can happen that this path can visit the alpha at this level, this path can visit at this level, this can visit at this level, right? So it can happen that, so maybe all the paths are good, so they are visiting, like if it's an accepting run, all the paths are good, but they may not visit that the alpha states at the same level, right? So what I would like to do is essentially, like whenever I am visiting, like suppose these are my set of states. Now whenever I have visited this particular set, this particular path has visited an alpha state, I'll say that this is good, I'm not going to keep track of this anymore, so I'll have only this one and this one. Now, when this one visits the alpha states, then I'll have only this one. This one visits the alpha state, then I'll only have, I'll have none of them, because all of them have visited.
We should also make sure the alpha states are visited infinitely.
Exactly. So the alpha states are visited infinitely.
Now the yet to reach part will have the alpha states that it has visited.
The yet to part is the one which is yet to visit the alpha state, right? So it can happen that when this one is visiting the alpha state, meanwhile it can also happen that this guy has visited the alpha state maybe even a couple of more times, which I'm not really bothered about because I'm talking about visiting them infinitely often, right? So as long as I'm saying that all of the paths are visiting the alpha states, I'm fine.
So after we have seen alpha states once, now we will check whether it's visiting again, kind of.
I'll check that whether I'm going to. So here, so in one component, in this component here, I'll keep track of all the states that I'm seeing at a level. And in this component, I'm going to see, I'm going to keep track of those states which are yet to visit the alpha state, right? So I'll keep kind of, so this part will kind of keep reducing, okay? And this side, right? So if I have, for example, let's say something like S comma R, so one thing to just to note is that my R is going to be a subset of the S. Okay, so this is just one thing. So to start with, so my initial, so this is how my automaton will look like. So I'll keep my automaton this A prime. I'll say this is 2 raised to Q cross 2 raised to Q. I have the alphabet sigma. Then I'll have the initial state Q0 and cross, I'll start with an empty set. Okay, I'll start with an empty set. And then what should be my final, what should be the good states here?
2 power q plus 5.
2 power q plus 5, very good. So this is 2 power q plus 5. So when all of them, they have visited, right? So I'm gradually removing things. So here I have visited, I will no longer keep track of the this path, right? And then when I'm visiting this thing, I will no longer keep track of things that are going like this. And then at some point of time, this part is going to be empty, which means that somewhere in the past, like all the paths, they have visited alpha. And then I need to reinitialize. Okay, I need to reinitialize to my new set of states. Maybe new set of states minus if this new set of states, if some of them are already alpha there, I'll get rid of those alpha and then I will reinitialize. And then I'll try to visit that continue until the second component again becomes the empty set.
So shouldn't the initial state be Q naught cross Q because we over visit to all the states?
But we haven't seen any states.
So yeah, I mean to start with,
It should be q naught come across q naught, right?
Yeah, exactly. Because the second component will tell what all we have to visit.
Q naught owes a visit to alpha.
I can also make it Q naught cross Q naught. It doesn't really matter in the sense like, I mean, you can make it anything. In the sense you can also make it, let's say, so what I would like to do is, so this part, I would like to say that this should be a subset of this part. So this invariant I would like to maintain. I can also make it Q naught cross Q naught as you were saying. So it's also fine to have it like this, okay, to start with. But given the fact that why it does not make any difference,
I meant Q naught cross Q because we over visit to all the states.
But not all the states might appear in the.
yeah, so the reason being, like what I'm saying is that at every level, what I'm having is like the set of states that in the run, so there is a run here, right? So there is this run. At every level in the first component, I am seeing what are all the states at these levels, right? At every level, this is what I have. And the second component says like which of these states have kind of visited the alpha.
Okay, okay.
So the second component is going to be a subset of
Right.
the first component.
Yeah.
Okay. So now I'm saying that, okay, I could have as well kept it like this, Q0 cross Q0. but it's also fine to have it like U0 cross the empty set, in the sense that because I'm talking about like this being visited infinitely often, so I can kind of reset and then I mean, this is okay to have. Okay. So, yeah. And the thing is that, yeah, the transitions will show in a while that whenever I have them empty, what I will do, I will reinitialize it. Like, so suppose if it is empty, then whenever so I'll see what are the set of states I'm going to in the next level, and then I will, if this is empty, then I'll reinitialize it to those set of states, maybe with the alpha being removed, alpha states being removed. Okay, so that's what I'm going to do. So let's see. So let's say I call at any point, this is what I'm calling the set of states as S comma R, right? And so, I should have a delta prime somewhere. Let's say this is the delta prime. So I'm going to define the delta prime, right? Define delta prime. So how should I define delta prime? So delta prime, comma, delta prime of S comma R, AR. So what is this? So S is a set of states, right? And so, so I'll call them, let's say, S prime, comma, um, S prime, yeah, okay, and R prime minus alpha. Okay, so what is S prime here? What is S prime?
Delta of S prime.
Delta of S comma A. But delta of S comma A, it means actually like, it's actually the conjunction of Q belonging to S, delta of Q comma A, right? So this is what. And similarly, R prime is delta of R comma A, which is the same as like Q belonging to R, delta of Q comma A.
So if the transition was
Yeah.
say Q1 or Q2,
Yeah,
then it suffices to check that Q1 is satisfied or Q2 is satisfied, right?
yes.
So, like, there should be a component here also which will do it separately for you.
There will be a component. So what you are doing is that then this will be different runs, right? There will be different runs, correct? And then when you have here the non-deterministic automaton here, the A prime that we are having, so you will also have like the corresponding this the subset will correspond to only those set of states which corresponds to one run. Okay, corresponds to one run. So the NBW is trying to guess an accepting run.
Okay.
Okay, so you have all these different possibilities, all these different valid possibilities you will be having. So the NBW is going to guess such a run, and what it is doing is like whenever you have this R, you are going to have this R prime, but you are saying that if you already visit some alpha, then I'm not going to have that, I'll have those states anymore, right? I will just keep track of those states which are yet to visit some state in alpha, right? So now the thing is that this part comes like whenever, let's say, what happens if at some point of time, so this is if R is not empty. Okay, and what happens if R is empty? So what would you do if R is empty?
Then you would have S prime comma S prime minus alpha.
S prime comma S prime minus alpha. Okay. Okay, so S prime comma S prime minus alpha. So now you see that it can indeed happen, like as I was saying that because here I'm saying that, so this is the part where, let's say initially, suppose R was, let's say it was, the second component was empty. And so I initialize it to, in the next level, I initialize it to S prime comma S prime minus alpha. And then it can happen that this second component is always now keeping track of the second component at the previous level, right? And it does not bring in states from the first component S, right? Until this second component becomes entirely empty, right? So it can indeed happen, like for example here, when you see a good state, in the second component you no longer keep this particular, the state corresponding to this visit of alpha. And it can happen that in the run, when you are visiting let's say this particular alpha state, it can happen that meanwhile you may visit something good here also, but we don't care really, right? So this is the translation. Okay, is it clear?
Yeah.
So we have these two components. The first component is keeping track of all the states in every level of the run. So there can be multiple possible runs, and it's just that the non-deterministic automaton will guess such a run. Whenever you have a disjunction, this will correspond to different runs, and the NBW is going to guess one such accepting run. Okay. And in the second component, I keep track of like all the states which are yet to visit good state, right? Every time I'm visiting, I know that I have visited all the good states, then the second component becomes empty, and then I sort of reinitialize it, right? I reinitialize it, and then again I continue until I find that, okay, all the paths, they have become, all the paths have visited the alpha states, right? And here there is one thing that we should just note, that it can happen that when you are talking about these different paths in the run tree, this is something we have, something we possibly have noted, but I did not mention it explicitly, in the sense that there can be, when we are talking about several paths in the run, there can be infinitely many possible paths, right? But at a particular level, you only have n many states, where n equals the number of states of A, right? So there can be at most n many such distinct states, right? But at a given level, it can happen that many of the states are getting repeated, right? Arbitrarily many times, the states are getting repeated. But here the assumption is that, like, all the states, they would proceed in the same way going further, right? So this is something which we are assuming, and this is indeed, one can show that if there is an accepting run, then there exists an accepting run such that all the states would evolve in the same. It's not very difficult to sort of imagine, and indeed one can formally prove this. And this is what is called a memoryless accepting run, in the sense that you don't need to really think about the history, like along from along which states I came to this particular state, right? It can happen that when I'm reaching, suppose this is a state Q, this is also a state Q, it doesn't really depend on what the history was, how I reached this particular state Q.
Because now we just want an accepting run, and
You want to
after this you
accepting
could
run,
just-
and the future only matters. How you reached there doesn't really matter. Right? So this is just, we all understand, but I just wanted to mention it explicitly. Okay, good. So this is the Miyano-Hayashi construction, right? So you get an automaton, an NBW, with the state space of the form 2 raised to q times 2 raised to q. And one thing to note is that, like, if a state is of the form s comma r, then r is a subset of s, right? So this is clear. R is a subset of S, right? Now, if I ask you what is the size of A prime? What is the size of A prime you have?
There are 2 to the q plus 2 to the q many and because of this condition, some more things are relevant. It's like summation of S into 2 to the S, where S is a subset of.
Mhm.
Uh,
But there may be an easier way to compute this number. You consider in terms of every element, like what are the different combinations you
It
can
could
have.
either be in both R and S or just S or none. So 3
okay,
pi.
3 power k.
3 power n, right?
Okay, yeah.
Okay. So this is indeed the number of states is 3 raised to n. So so it gives you an NBW with 3 raised to n states. Okay. And again, there are these lower bound proofs. One can show that, like when you are doing such an alternation removal, right, ABW to NBW, when you are doing such an alternation removal, one can even ask, like, is it really necessary, right? You are doing this ABW to NBW. Is it really necessary that you need so many states? And it can be shown that if instead of ABW, if you just start with a universal automaton, then itself you can show that this blow up is inevitable, right? So universal automaton, like you have only the conjunction. Huh? So even if you start with such a special case, then itself this is inevitable. Clear? Good. So this is the lower bound appears in this paper, in Michael 2010 paper. Now, okay, so here is a quick question for you. So given that we have seen all these translations, can you show that NCW is no more than DCW? So suppose if I, instead of an alternating Bushy word automaton, ABW to NBW is what we did, right? Suppose this is related to what you were asking. So suppose instead of an ABW, I start with a UBW, universal Bushy word automaton, where you don't have the disjunctions, right? You only have conjunctions, correct? So what will be the resultant automaton that you get? DBW, right? So if I start with an UBW, and then if you do the image construction, Miyano-Hayashi, you get a DBW, right? Right? So now, can you try to answer this? Can you show that every NCW can indeed be translated into a DCW?
So we can consider the NCW as an alternating automata and just dualize the alternating automata to get
Sure. To get
an alternating co-Bushy automata.
okay.
Which is
And since it's a special case of an alternating automaton, so you are right. So you can consider this as an ACW, right?
yeah,
Okay. And then
we'll get an ABW by.
you can get an ABW, right? You can get an ABW, but this is a special case of an.
Yeah, this will be universal because the NCW was existential only.
Okay.
Yeah.
Now this takes the L bar. So the NCW, you can look at this, the same automaton, the NCW, the non-deterministic Kobushi word automaton, just by dualizing the acceptance condition, you can look at it as an UBW which accepts the complement language. Why? Suppose, okay, so let's say there is a word W which is W belongs to, suppose I start with an NCW A. Suppose W belongs to A. So what does it mean? There exists an accepting run which will visit alpha only finitely often, finitely many times. Right? So there exists such a run. Right? And in the U, if you look at this as an UBW, where all paths should visit alpha finitely often. So all paths infinitely often. So of course, this word W will not be accepted by the UBW when you switch the acceptance condition, because there exists some run, right? If W belongs to A, which is an MCW, there exists a run which visits alpha only finitely often, alpha finitely often. Right? Now you look at it with the same alpha as a Bushy automaton, right? So clearly it's an universal Bushy automaton, UBW. Clearly W does not, so if I say A prime, W does not belong to A prime. Okay? And similarly, if W is not in A, suppose W is not in A, so then what does it mean? There doesn't exist all the paths, all the paths that you have, all the runs of W in A, in the NCW A, they visit alpha only.
They visit alpha infinitely.
They visit alpha infinitely often. They visit alpha infinitely often. Now you look at it as an UBW. It's accepted, right? So W belongs to A prime, right? So the UBW accepts the complement language, right? Now you can get a DBW. You do the image, you get a DBW accepting what? Accepting L complement. Because the Miyano-Hayashi construction just removes the alternation, doesn't change the language. Now what?
Now DCW will accept it.
Now you again do exactly the, look at this DBW, but look at it as a dual acceptance. So you get a DCW. DCW, and the DCW is going to accept L, right? So starting from an NCW, you can get a DCW, right? So NCW and DCW are equally expressive. Clear? NCW and DCW are equally expressive. Okay. Now, what about all these things? Maybe I should also add here UBW, UCW. So what do we know now among all these things? What do we know? NBW, DBW, we know this much, right? We know that ABW is the same as NBW, right? And DBW is strictly weaker. Okay. NCW equals DCW. What about UBW? We know that this is UBW, right? We just saw this. This is a Miyano-Hayashi, right? Just by image, right? And here also this is image. So we know this thing. What about ACW? Or UCW, what do we know about them? What do we know about ACW?
Will UCW also be as expressive
as
DBW and DCW and so on?
DCW. Why? What about, okay, let's
Wow.
talk UCW.
DBW.
Yeah, anybody?
No. That's
What about UCW? What is the expressiveness? Yeah.
I guess for ACW first, we can convert it into a weak alternating automata, and hence,
Okay.
so we have one inclusion that it is.
ACW
Yeah.
can be converted into a weak alternating automaton.
Yeah, and the other way is also true because ABW to ACW is also there. So it is true that ABW equals ACW.
ABW to ACW, there's a complementation happening.
Okay, that's a complementation.
Yeah.
But the weak alternating automaton can be thought of as a Kobushi as well.
Yes. Sure. Yeah.
So ACW equals NCW.
ACW equals NCW.
But NCW
Yes,
is
absolutely.
just like
Yeah.
ACW like with dialysis.
Sorry, could you repeat?
NCW can be thought of as a ACW, right?
NCW can be thought of as a special case of ACWs.
And ACW to NCW this.
Like,
Well, how did you get ACW
Because
to
we
NCW?
automated, we can consider as a coefficient.
No, we got this thing. We got NCW to DCW. We never said like the entire ACW can be translated, right? We just said if you start with an NCW, then it is like a UBW with the accepting the complement language, get a DBW, and this is what.
No, NCW is also an ACW, right?
NCW is a special
Huh.
class of ACW.
Yeah.
Yes.
But ACW can be converted into a weak automaton,
ACW can be converted into a weak automaton.
which can also be seen as a co-push automaton.
Alternating.
Right.
It's an alternating automaton. Right?
It's just a subset.
Because you recall that when we did that translation, we used a release operator where there was this. We started with an alternating solution automaton. We used the release operator, it added some disjunctions and all. And all the delta function, the delta transition function was there. What about the UCW? So suppose, let's see. So, okay. So suppose you have, there is an UCW, it accepts a language L. Okay. So all I'm saying that can you get an NBW from this? And vice versa?
So you can complement it first,
Sure.
and that will be, you can see it as an NBW. And NBW, you can now complement NBW.
Yeah. So we know that NBW are closed under complementation. Right? So NBW, it's closed under complementation. You can get an NBW with language L.
And
right?
Suppose we have an NBW with L. Can it?
And
It can, yeah.
and you can exactly do the other way around.
Yeah.
Like given an NBWA, you can also get an NBW, or you can consider this as an ACW L bar, UCW L bar. What are we trying to say? We are trying to get, yeah, I mean, we can exactly do the other way around, right? NBWL bar you can get, and then this can be seen as an UCW. Right? So UCW and NBW are equally expressive.
NBW and NCW are not, right?
NBW and NCW are not, or are they?
Like if they're not, we are done. Then we know UCW is strictly stronger than NCW.
So what we know is that NCW is the same as DCW.
Huh.
This is what we know. And we have also now seen that UCW is the same as NBW, right? So UCW is the same as this. So what is remaining? We have seen UBW, we have seen UCW. Now ACW is remaining. Okay. Now, can you translate an ACW to anything, to an ABW or anything? Because we now have everything else.
Yeah.
We can translate it to an ABW. Yes.
ACW to an ABW. How?
Because
ACW
can be
To a
can be
weak
translated
alternating.
to an ABW. ABW, so this is the translation we already saw. It's a weak automaton anyway we can do, right? The quadratic translation, weak. It can also be thought of as an AC, as an ACW, right? So this is a weak automaton, right? So ACW can be translated to an ABW, right? Now the question is that is then ACW, ACW can be translated to an ABW already, right? A special kind of this thing.
Yeah.
ACW is clearly more syntactically more expressive than, so ACW is at least as expressive as UCW.
Yeah.
Right?
Yeah.
And also the ACW can be translated to an ABW.
Right.
Right? So what do we get? Equivalent.
It's equal. Yeah.
Clear? Because the UCW is the same as ABW. Right?
Yeah.
So this gives that ABW is at least as expressive, and this gives that ACW is at least as expressive. So this gives, so here we have ACW, UCW, and here we have, because of this, we have ACW, ABW, right? And we also have an equality here. Correct? So that means ACW is the same as ABW. So this is what we have. Clear? Anything we are left with? What we are left with right now?
Relating the two things.
Yeah.
Relating the two things, right? So which two things?
NCW and maybe
NBW, let's say if we talk about NBW and DCW, or NBW and NCW, NBW, DCW, right? Can you say something NBW and DCW, let's say, or
complement.
what can you say? Okay, I think, yeah.
Complement. So DCW, consider that as an NBW, then you get complement language. But
DCW, you can consider that as an
NBW with the same alpha, then you get the complement.
DBW.
Huh. which will be DBW, but
Right.
now you take the complement of it, which will be an NBW.
Okay.
So it's close. The DCW is a subset of.
So what are you saying is that like, so if you start with a DCW,
Huh.
let's say,
So it has exactly one path for each word.
so DCW, let's say it accepts L, you can think of this as an DBW,
DBW, yes. With
which
L.
accepts L bar.
Yes. Now take the complement of it, which will be an NBW with language.
Okay. Okay. So you can get an NBW.
With language L.
You can complement the DBW we saw, right? And then you can get an NBW which accepts L. So DCW
Is a subset of L.
is a subset, right?
Well, no, I don't think it's going to be the other way.
Huh. So what we have is like DCW is a subset of NBW. Okay. So now we need to see if it is a strict subset. Okay, so this is something we have. Anything else that is left, or that's
We
all?
need to relate it with DBW and UBW.
So what about if DCW and DBW? Okay, so this is also something we would like to know. Okay, so okay, so these two we have to do. So what are the languages that we saw earlier? Let's see. So let's say so is it, and the other thing is if this is the case. Clear? Right. So I think let's try to answer one of them. I assume that we'll get the answer for the other one. So let's try to start with this one maybe. Okay, if they are equivalent. Huh? So what languages do come to your mind?
Finitely many zeros.
Finitely many zeros. We were talking about finitely many A's. I mean, we were. I mean, you were right. I can have 0, 1 as the alphabet, or equivalent. I mean, I can also think of A, B. We were just following this thing. They are the same. So finitely many A's, or right. So let's see if we can do something with this.
So that's a DCW,
but
for
not a
that,
DBW.
but not a DBW.
There is a DCW for finitely many A's.
Yeah.
Right? So how do you draw that finitely many? So let's say we have the
Yeah.
right. So this has like if you consider this as a DCW, then it accepts finitely many A's. DCW accepting finitely many A's. Clear? There is a DCW which accepts finitely many A's. Okay. Now we know that this cannot be accepted by
DBW.
cannot be accepted by a DBW. So then there exists some language which can be accepted by a DCW but cannot be accepted by a DBW. Now
By DBW, but not by DCW.
so I thought this is clear, no? Oh, okay, like a strict subset, right? So there is, so this is Okay. So finitely many. Okay. Then what about the complement language? Now, infinitely many A's.
So DBW is there, but DCW.
Okay. So
I don't think.
Yeah.
suppose there exists some DCW. Can we? Okay. So how can you prove that? So we claim. So our claim is the following: that we know that for this. Okay. So we know that for this DBW exists. Which one is the DBW? This itself. If you look at a Bushy acceptance, this accepts infinitely many A's. Clear? So a DBW exists. So if we want to claim that DCW does not exist, claim is that DCW does not exist for this language. Exist for infinitely many A's. Okay? Right? Yeah. Then we will have this answer. If we can prove that, then it will answer this. And it will also answer this. Clear? That they are incomparable. This will be answered like they're incomparable. And it will also show that indeed there exists, like we have proved this, that DCW is a subset of this thing, and if we have this that does not exist for infinitely many years, then it's a strict subset. Clear? So how do you prove this? Suppose there exists a DCW with infinitely many years. You can come on, I mean,
This is giving some looping thing.
Yeah.
So, so the good state will, after the good state, A omega will be accepted.
Yeah.
Without going to the good state infinitely. So it should go to some bad state. And then
Like if we look at the set of good states, like alpha states,
Okay.
that is state of non-alpha states,
Ah.
we know that there is a path from the good states to the bad states with just A.
Hmm.
And there's a path from the bad states to the good state with just B.
Hmm.
And now, so we'll just take those two paths and do omega.
A B omega.
So that will actually have infinitely many years, but
But
still
still, it's
not
not
be
good
accepted.
You are right. Okay, but I mean the same argument as we saw, similar to what? Like there doesn't exist a DBW for
Finitely many.
many
Yeah.
years.
Same argument.
Same argument.
Yeah.
But do you really need that argument? Okay, claim. Okay, so for contradiction, suppose
After some point, it should stop visiting the accepting states, but say that some point is K.
this
But
is the
Yeah.
DCW that accepts infinitely many years. Infinitely many years. Then
at some point, as he said, like at some point it should stop visiting the good state.
without going into that argument, then looking at it as a DBW,
The complement automated will accept finitely many A's. And it'll also be a DBW, so which is a contradiction.
you got it, or should I say again? Suppose there exists a DCW which accepts this language of infinitely many A's.
Okay.
Look at this DCW, look at this automaton with the dual acceptance, then
So you're swapping the accepting and non-accepting.
no, by dual acceptance, I mean like looking at the acceptance condition as a bushy acceptance instead of a co-bushy acceptance.
So we want the words to be accepted, or which have finitely many A's, and we know there's no DBW for that. Okay.
So now you got it.
Yeah.
So suppose there exists a DCW that, so for sake of contradiction, there exists a DCW that accepts infinitely many A's. That implies that there exists a DBW that accepts the language of finitely many A's, which we know is not true.
Yeah.
Right? Hence, there doesn't exist. Right? So this implies there exists a DBW that accepts finitely many A's. Okay, which is not true. And this is not true. And hence contradiction. Right? Clear? So do we now have answers to all these questions? So there is something accepted. So these are incompatible. DCW and DBW are incompatible. Right? And DCW is a strict subset of NBW because infinitely many A's cannot be accepted by DCW. Okay?
Yeah.
Clear? So we have answers to all these questions. So I don't think I have written this anywhere, but like it's recorded now. So good. This is not exactly in this form. It's there in those notes, but I mean all the results which are there in those notes you can just figure out yourself. Nothing like you don't need any complex construction or anything of that sort. Like whatever we studied, we can just derive out of them. Okay, good. Now here is a question. So we saw this construction, right? Alternating Kobushi to this weak automaton. And we said that there is a quadratic blow up here in this part. There's a quadratic blow up. The question is this, can this quadratic blow up can be reduced to a linear one? It's written here. Now you have to just tell me like right? The answer is that it's not possible. And I have written it why it is not possible. You have to tell me why it's not possible. Based on like all the things that we have learned. This is MH, stands for Miyano-Hayashi.
ABW to ACW, there is no blow.
No, no.
Right.
ACW, and we know the final blow from ABW to NBW is exponential. That we can't avoid.
There is a lower bound on NBW complementation. So
Yeah. So if you do this, then what is the blow up that you are getting?
3 pi.
This is okay. So let's see, you are right. Maybe if assuming, suppose if this is linear, if this is linear, if linear, then you get a blow up of like let's say 3 power order n, right? So you get 3 power order n for the complement language.
Yeah.
L bar. Right? Whereas as Vishal was saying that we know that there is a lower bound with 2 raised to n log n. lower bound for NBW complementation, right? So you can, so what is the idea? So let's go through this. Suppose you are given an NBW and you are given an NBW, you can look at this NBW as an ABW, right? And then you do this series of translations. So you look at the ABW as an ACW. So the language is L bar. Look at it as then do the translation to weak alternating automaton. Suppose we make this claim that this is a linear blow up, and then you do the Miyano-Hayashi. You get an NBW, right, which is of the size 3 raised to order n. It accepts the complement language of the initial NBW. If you start with an NBW accepting L, you get an NBW accepting L bar, and this has a size of 3 raised to order n. Now we know that there is some lower bound which has 2 raised to n log n for NBW complementation, right? So clearly, such a translation cannot be true. Okay, so this gives you the answer to this question, that this cannot indeed be reduced to a linear. This
But then it's just saying
Blow
we
up.
can't reduce it to linear. We are not telling anything about like.
Yeah, we are not saying anything more like here. Nothing about n log n or something of that. We are just saying that the n square cannot be reduced to n. Okay, so now we will talk about this non-emptiness problem, the complexity of these things, right? So we started with, indeed, like we said, that why do you need to talk about sometimes this alternation removal? Because certain things may be more difficult to deal with in the case of ABW. If you look at non-emptiness, it's not so easy. So what you would do is you would change it into a non-deterministic boogie word automaton and then check its emptiness. Okay, so that's an algorithm, I'm saying, suggesting an algorithm. So what is the complexity of that? What is the complexity of, like, if I do this procedure, translate it into, it's an exponential time procedure, but you can also do the construction on the fly and then do the non-emptiness check, right? And the non-emptiness check is like, it's just that going from an initial state to a good state and looking at its loop, which can be done in n log space. And if you do it on the fly, then you can pretty much do the whole thing in p space. You don't have to store the entire that non-deterministic bookie word automaton. You do it on the fly. Only the parts, part by part, like only the parts which you need, you guess that it's a non-deterministic p space, and by Savage's theorem we know that it's same as p space, deterministic p space, right? So you can guess part by part, like, okay, this is the next state that I need to compute and so on. So essentially you guess the path in that non-deterministic automaton from an initial state to a good state, and you also guess a path, and then you kind of do this in polynomial space. Clear? So we have a p space upper bound for the non-emptiness problem. What about the okay, so let's, before we get into the lower bound, what about the non-universality and containment, etc.? So can you check the non-universality also in p space? Non-universality of an ABW? Using the non-emptiness?
Yeah, we can, or just complement the ABW using
And complementing the ABW, what is the blow up?
it's okay.
What is the blow up for complementing ABW?
Because we just make it
Quadratic.
It is a quadratic blow up we saw, right? Like,
Yeah.
just this construction that we did last time, no?
Yeah.
So what was that here? So we started with this today. No? Here is the blow, no? ABW to ACW, and then this is what we have been doing, right? It was that ACW to ABW, that that we guess that ranking function, right? So it was that q cross 2n, that set 1 to 2n, like it's a quadratic blow, right? So this is, so you have a quadratic blow, right? So accepting, so you start with an ABW, you get another ABW which accepts the complement language, and it's only a quadratic blow up, still a polynomial blow up. So if you have that, then now if you are asked for checking non-universality, what can you do?
Check non-emptiness.
Check the non-emptiness. Check the non-emptiness, and everything you can do on the fly, right? It's actually, you just guess non-deterministically the complement language, and also the once you sort of get the non-deterministic automaton corresponding to that after removing the alternation. So everything you can guess and then do everything on the fly and get a piecewise algorithm. What about the containment? Like given two ABWs, like whether one is contained in the other, the language of one is contained in the other.
Complements of both, and we can do intersection, right? And just add.
Yeah.
Right.
So we'll do the intersection and check if it is not.
So the complement, so if it is like A1 subset of A2, is this is what you want to check, right? When I say it's like language of this, right? Language of A1 is a subset of language of A2. You just take the complement of A2, right? And take the intersection.
Yeah.
Right?
Okay.
And the intersection for ABW, it's very easy.
Yeah.
Right? We saw that. Take the, as you said, take the, and you just have a new state and take the conjunction as we saw. Right? And everything can be again like it's all polynomial. The size, everything you can again do on the fly and do things in piecewise. Right? Good. Now, what about the hardness? What about the hardness of non-emptiness?
NBW universality is piecewise.
NBW
Universality is
piecewise hard. Good. NBW universality is piecewise hard. Good. Or yeah, non-universality anyway is piecewise complete. We saw that. So can you reduce this problem to ABW? To ABW non-empty.
Non-universality though is direct because you can see ABW as in, sorry, NBW as an ABW. And if that can be done, this can be done. But non-emptiness. So non-universality, we can directly say it's piecewise complete. But for non-emptiness.
We can complement the ABW
Yeah.
the same manner.
So what do you need to do for this reduction? So given, suppose you are given an NBW A, okay, you have to, so just look at the reduction that we would like to do. We would like to construct an ABW A prime, okay, and we would like to say that this is non-universal if and only if this is non-empty. Okay, and this reduction should be a polynomial time reduction.
So just take the ABWA.
Yeah, so this you can consider this as an ABW also, A,
And then do the complementation, which will be quadratic.
which will be quadratic.
And now you can.
Now you can, so this is universal and right, so you can think this is a quadratic translation, right? Polynomial time reduction. Good. So we have the hardness.
Containment was from universality.
Yeah.
suppose containment is P space, sorry, it can be solved, then you can just check if sigma omega is a subset of LA,
Yeah.
then you'll get.
Yeah.
So all the other things are similar. We have
Yes.
seen them, right?
So,
Okay. So I think
Mm.
this is clear, right? All of them. Good. So what is the time? So we have 10 minutes left. Okay, good. So I had a question earlier. Is there an NCW for infinitely many? Yes. What is the answer? Why?
because NCW and DCW are equal.
Because NCW and DCW are equivalent. So that is the first thing. And then you say that if there exists an DCW for infinitely many years, then there exists a DBW for finitely many years, which doesn't. Okay. So, yeah. Okay, so I'll just start with, I would say, the next part of the course, essentially. So we call it automata verification and infinite games. So now we'll get into this verification part, right? So what is the idea of verification? So the idea is that you have been given some specification and you have a system and you would like to check whether the system satisfies the specification, right? So the system, we often also call it an implementation. So the implementation satisfies the specification or not. So the specification is given in terms of usually a logic formula, and the system is, it can be, let's say, a transition system, and there are different kinds of formal models people use. So one thing that people use, it's also called a Kripke structure. Okay, it's also called a Kripke structure. So you should see who Kripke was. Okay, so it's also called a Kripke structure. So what is the difference between a Kripke structure and a transition system? Usually on a transition system, we have the transitions on the labels, whereas on a Kripke structure, we have the transitions, we have the labels on the states. Clear? So in a transition system, we have the labels, like you have, for example, you have like in a transition system, this transition is labeled by some label A, letter A. Here, now I will say on the states, I will have some, let's say some A comma B or something like this. Here it's C comma D. So that is what usually in the Kripke structures, they are, it's like that. Clear? And there are certain, instead of states, traditionally these are called words. These are called words. So you move from one world to another world. Okay. There are transitions. Okay. And you move from one world to another world. Instead of saying that you have a set of states, you say there is a set of words. And there is some initial set of words. And so on. Okay. And in this course, we are going to look at verification of these reactive systems. Okay. And even before that, like when we talk about this program verification, in general, this can be undecidable. Like if you talk about, let's say, a Turing machine, right? If you talk about reachability in a Turing machine, like whether you can reach a particular configuration or a state in a Turing machine, I mean, you can show that this is indeed undecidable. Like it's just like the halting problem, you can say whether it will reach the halting configuration or not, it's undecidable. So anything which is like kind of very expressive, like which can simulate a model, which can simulate a Turing machine, so that is undecidable, right? So for example, if you talk about things like two counter machines, which you know can simulate a Turing machine. So if you talk about two counter machines, reachability, etc. So if your model, if your system model is a two counter machine, you cannot do much with it, right? I mean, so your model, abstraction of the model should be good enough so that your verification problems, algorithms, they are tractable, right? So you have to find the right abstraction also. So that is also very important. So can you, for example, like your system, can you describe it with the help of an automaton rather than a Turing machine, right? Because you cannot do much with a Turing machine. If you can describe your system with the help of an automaton, then you know that it's good. Or if you say that you want to model it with a Turing machine, then you have to restrict the resources that it can use, the amount of time that it can use, the amount of space that it can use, and so on, right? Or there can be other computational models, just like an automaton or some kind of a stack machine that you can use to model your system, right? Then you can do your verification because they will be decidable. Sometimes they may even have very high complexity, right? For example, if I give you an MSO, monadic second order logic formula with some system which is modeled as a Bushy automaton, we know that things can be like a tower of exponentials, like that much of complexity you can have, right? So the idea is that like we make several assumptions on the program so that our models are also to that much, like we put that much of restriction so that it's we can at least get some decidable algorithms with possibly good complexity and things like that. So that's the idea. And then what a reactive system? So these are not like our traditional algorithms where you have an input and it gives an output and it stops, right? So the reactive systems are systems which like interacts with the environment. You get an input, it gives an output, and it continues forever. Like so, it's some infinite interaction, right? As all this that we have seen so far, like our Bushy automaton, etc., right? Rabin automatons. These are automaton over infinite words. So we are going to essentially talk and reason about these systems which will have infinite truths, and they're very common. Like they're very common. For example, like you have some operating system which is running, some server which is running for a long time, giving inputs, producing some outputs. Like you consider your satellites, artificial satellites, which have plenty of sensors. They are sensing images, sending, and they may have some actuators and things like that, and communicating data and all. So these are all examples of reactive systems. So and several plant controllers. For example, the AC controller that you have in this TIFR building, right? So it runs forever, and then you have a controller somewhere. Sometimes you have, and then you try to control the temperature, right? So and it will, so based on your input, accordingly the plant will behave, right? So these are called the plant controllers, so which are also examples of reactive systems. And we are going to talk about model checking. If you recall that we also talked in the very beginning about synthesis, like how do you synthesize the controller itself? Given a specification, how do you synthesize a controller? So that is about the synthesis part. Here we'll talk about, to start with, about the verification of the model checking, where you are given the system. So that means like the plant is given and we want to verify whether the plant is behaving as per the required specification, right? So that is the idea of the model checking. And we will use, instead of like, so all these specifications will be given usually in terms of a logical formula, and often we use a particular logic which is called linear temporal logic instead of this first order logic or monadic second order logic, because they may have very high complexity, whereas we'll see that the linear temporal logic has much better complexity and can be used in practice. That's why. And indeed, you can also ask these questions. Like, for example, if you have seen two logics, are they like just like automaton, right? Like given exactly given two automaton, different kinds of automata, are they equally expressive, or what is their sort of succinctness, right? Like whether one form of automaton is more succinct than the other, if the expressiveness of one is more than the other, or they're comparable, incomparable. So we were seeing all these things, for example, today. Similarly, you can also ask the same questions for logic also, right? are these logics equally expressive? So for example, you have seen first order logic on words, you've seen monadic second order logic on words, and now you are going to see linear temporal logic. So a natural question that should come is like, are these logics equally expressive, or one is more expressive than the other, or can it be the case even if they're equally expressive or not? I mean, some properties can be expressed more succinctly compare in one logic compared to the other, right? So these are the kind of questions that one would like to ask. So we'll study linear temporal logic, and I think we will start with, like, for every logic, as we have a syntax, semantics, and things like that. So we'll start with that, and so in the next class, which is on Friday at 9:30, we will start with linear temporal logic. Okay, and that verification part and so on. Okay, so any question?
No.
No? Okay, good. So then I'll stop the recording.